action.
All right, everybody, thank you for coming to our presentation. We're all talking about managing edge security, computing security, and reducing exposure. This is for EE 640 communication protocols for the University of North Dakota. And I just want to introduce myself. My name is Keith Krawza. A little bit of background on me. I got a Bachelor of Science in Electrical Engineering from the University of North Dakota. Go Hawks. 7 years with the U.S. Army, signal and communications experience there. I'm currently employed as an aerospace engineer in the defense industry, and I'm getting my master's of cybersecurity and hoping to graduate this December.
Thanks, Keith. And I'm Steve Harris. A little bit about me. I have a Bachelor's of Science in Telecommunications from Fort Hays State University. I'm an author for a magazine called Broadband Library, where I author articles in fiber optics for 8 years. I worked in the telecommunication industry as a telecommunication engineer for the last 18 years. And I'm hoping to have my master's of cybersecurity a little later than Keith, December 2023. So we're going to get started. We're going to start with an introduction to our topic. Our topic is managing edge compute security and reducing exposure. So edge computing introduces a great deal of business complexity and will impact a large range of folks that support business infrastructure. So we felt it was a very important topic to discuss. Now, the technology is still in its early stages, and that's where we came in is look at the security models because they're not yet mature either. And this is the reason we chose the topic. So let's start looking at edge compute. So edge computing, as you can see here on the slide, has many different components from cloud computing, data center, access network, edge node, and IoT devices. So what we refer to edge computing is a network that utilizes a collection of layered technologies. Everything from communication protocols that we learned in our course, cloud delivery models that are distributed, and data processing techniques that are often not using fine-grained security. And so this is why we chose the topic. Edge compute is an open platform. That means that many vendors can design for it, but on the flip side, it's not standardized. And it uses multiple hardware platforms, software packages, and programming languages. So our research paper will examine edge compute security to reduce exposure to cybersecurity attackers. An edge compute deployment often lacks a strong security mindset. Folks sometimes take security for granted with these networks. It uses traditional coarse-grained security controls like firewalls or intrusion detection systems, not quite designed for edge computing. And it lacks a robust security framework. This is absent. So these are 3 areas that we're going to show in our research how to strengthen. To continue, in addition, it lacks standardization that I mentioned earlier, and this raises concerns for privacy. It also has data leakage concerns. This is important because these edge networks store a lot of personal data, a lot of configuration data, a lot of big data. Could be anything from financial data to bank data. These concerns pose risks for attacks that may concern for denial of service attacks, distributed denial of service attacks, compromised data, side channel information that can be used for jamming, spoofing, even zero-day attacks, as well as ransom or overprivileged attacks. So these are all areas that we want to do or we want to look at to reduce exposure. So our hypothesis. Multiple industries are distributing and virtualizing their network. And this is all the network's functionality using edge compute with cloud. It lacks a fine-grained security framework. and a framework that has a lack of protection, no privacy guarantees, and is at risk for a number of cybersecurity attacks. So how important is the issue? Here's a few stats that we pulled together. So IDC predicts that by 2025, there will be 55.7 billion connected devices worldwide. 75% of these devices will be Internet of Things. And Internet of Things is a majority of devices in edge compute. And another statistic, 2/3 or 66% of IT teams see edge computing as a threat to their organization. So there's some real issues with edge computing. So I'm going to turn that over to Keith to talk a little bit more about edge at the risk.
All right, thank you, Steve. So edge at risk, I'm just going to go over a couple practical examples of edge computing in our civilian sector and our military sector. So Steve, if you want to hit the next slide. As mentioned before, the civilian sector will see an estimated 55.7 billion connected devices worldwide by 2025. Three major areas where edge computing will be leveraged is in telecommunications, smart cities, and Industry 4.0. Customers in the telecommunications industry want higher data rates. The rate of smartphone ownership is on the rise, and it has been so over the last few years. Currently, nearly all households in America own a smartphone. As a smartphone user myself, I like having fast response times to media and the ability to stream high quality video on demand. And so mobile edge computing provides an IT service environment and cloud computing capabilities at the edge of the mobile network in close proximity to mobile subscribers. And as for smart cities, they're rich with opportunity to deliver smart power management. Edge computing is a key resource in developing this to enable intelligent response to demand through artificial intelligence, ML, and deep learning algorithms. And then lastly, Industry 4.0 is, in layman's terms, a smart factory. With the explosion of smart sensors, microcontrollers, and automated equipment, industry is processing more data of different types than ever before. Edge computing is being leveraged in the sector to improve network architectures such that data is processed faster and visualized better. Next slide. So the military sector and the Internet of Battlefield Things. What is known as the Internet of Things, or IoT, in the civilian sector is being coined as the Internet of Battlefield Things, IOBT, in military networks. And militaries have a distinct advantage if they can connect their warfighters and warfighting functions in these networks and leverage edge computing. The picture in this slide is just a great visual of a modern connected battle space. You can see munitions, sensors, wearable devices, robots, weapons, vehicles, the list goes on. Next slide. So the Internet of Battlefield Things and the edge. What are some specific examples of how this can be leveraged? One being superior intelligence. The more actionable data that a military force can receive from the battlefield, the more informed that command staff is going to be on decisions. Similar to how Industry 4.0 leverages edge and conglomerate data faster and in a more visual way for production settings, edge computing in military devices could present faster and better data to the warfighter. Friendly and enemy identification. This is huge for today's military. Positive identification of the enemy can be extremely difficult in real-time combat. This is amplified in urban environments, and opposing forces can easily be dressed as the same as civilian population. So connected sensors on soldiers processing unique physical behaviors and characteristics could reduce civilian casualties and fratricide in future war. Edge computing here would be especially critical to this function because edge computing latency is really low. Another key task that edge computing could accomplish is monitoring soldier physical and mental health. This would be a huge step for the military, allowing leadership down to the platoon and squad levels to see health-related measurements like hydration, blood pressure, G-force, exposure from impacts or blasts, and exposure to chemicals. All of these metrics could be life-saving knowledge. And then the last point is context syncing. In a secure edge computing leverage battle space, a warfighter would be able to do things that have simply not been done before on a large scale. Contextual syncing is a term I use to group capabilities such as a soldier could unlock a mounted weapon system or vehicle by walking up to it where it would otherwise be safely disabled, or feed drone data to his or her displays based on position. Next slide.
Yeah, excellent on that. So let's talk a little bit about these attacks. Keith did a great job of laying out some of the examples where edge compute is used. But pretty much all the major attacks are targeting edge compute, whether that's denial of service. Even worse, the distributed denial of service attacks are very prevalent in edge computing architectures. We mentioned the 0-day, but even worse, botnets. So where I can actually inject malware into devices and control them like robots to attack edge computing. Furthermore, there are AAA, or what we call public key infrastructure vulnerabilities that are weakened, and unauthorized privilege abuse. These both open doors for attacks. Since edge computing uses cloud, poor cloud security, we also have to worry about. And this will allow for web-based attacks, such as SQL injection, sequence query language, or even scripting attacks, because there's so many different programming languages. In addition, all these IoT devices that are listed here and the ones that Keith just mentioned have firmware. And whether that's the edge servers or the cloud computing devices, they are all running some type of software. So firmware attacks also target IoT devices and devices within the edge network. And lastly, we also have phishing attacks and spear phishing attacks using social engineering and trickery to attack the network as well. So looking for weak trickery to gain information from humans in the network. So listed here, the top 4 attacks were the denial of service, side channel attacks we mentioned earlier, malware injection, and authentication authorization, which is that weakened PKI. So some of the defense and countermeasures, the lack of a unified security framework that Keith and I discovered, and a lack of a layered defense model inhibits trust for decentralized edge networks. And cloud delivery models, as well as content delivery networks, or CDNs. A trusted computing model will strengthen overall security here to combat cyber attacks in edge computing. As a first layer of defense, the utilization of an embedded internal trusted platform modules 2.0. These are chips that provide a framework for identity authentication, trusted encryption, secure cloud access, physical to virtual machine mapping, and behavior tracking, all listed here in this diagram. A second layer of defense, Intel has a chip, a security chip, an SGX chip, that has built-in instructions similar to the TPM that we mentioned. This will give edge devices a basis for trust in the network because they can hide signatures or keys that provide authentication. Additional defense and countermeasures include blockchains, in particular private blockchains. It's a recent technology to provide a third layer of defense and trust for edge computing. Combine that with TPM and private blockchain, now we can have chains of trust for serverless edge computing systems like cloud and edge compute. Private blockchains improve public key infrastructure models that provide authentication, authorization, and accounting, or AAA, using secure digital certificates along with privacy. Employing superscale private blockchain data integrity requires quick hash calculations. Using quantum dot architecture will allow quick retrieval of data. Now I'm going to turn it back over to Keith to talk about CAAB tracking.
All right, thank you, Steve. Yes, CAAB tracking. So this is a novel approach that we found in our research to deter unwanted users from getting access to data stored on the edge. It's the long term for it is compulsory traceable ciphertext policy attribute-based encryption. We'll stick with CAAB. This is a traceable scheme to track the actions of malicious users. So to aid in fine-grained access control at the edge, ciphertext policy attribute-based encryption is used. This ciphertext scheme is encrypted in such a way that data may include an access level while not necessarily revealing data about the sender or receiver identities. In application, this could also be used to reveal malicious data being sent around if the attacker does not know the attribute-based ciphertext scheme. This can be related to a malicious person leaving fingerprints on a package and is an example of cyber forensics. An advantage to this method is that it is lightweight and therefore can be used on edge devices lacking in computational power and memory.
Yeah, and finally, Keith alluded to artificial intelligence and machine learning and deep learning techniques will provide that fine-grained security required by edge compute, as you can see on the left-hand of this slide. AI will also lead to better decision intelligence related to secure business results and performance. And to increase the robustness and the agility of future edge networks, we're suggesting the use of software-defined networks, or SDN, and supplementary network function virtualization, NFV, combined with cloud and a virtualized environment, will improve security at the network and transport layers. So back over to Keith for research methods.
Thank you, Steve. So for research methods, we used inductive research to develop our hypothesis and exploratory research to uncover more about our research problem. We applied this research to develop a security model and layer approach to edge compute security. We collected our data from various papers from IEEE, Elsevier, Wiley, IET, and Springer. And these are all well-respected publishers. We also performed quantitative and qualitative analysis using surveys and other things like that. We also used tools. We used several databases and also brought in and sprinkled in some current events, blogs and stuff like that around the issue. Our rationale for choosing this method was that we felt there was sufficient data for us to conduct our research and present a possible solution. Go to the next slide.
Yep, and here we will present our evaluation and some of our facts. Not to dive into all the detail here, but we have several approaches on the left-hand side. We talked about RF hopping, TPM, private blockchains with quantum dot. We talked about machine learning, deep learning, and artificial intelligence, reducing side channel information, CAAB, and finally, SDN and NFV. So Keith's going to talk a little bit about the limits and challenges to some of these approaches.
Thanks, Steve. As for limits and challenges, TPM acceptance as a global standardization, vendor acceptance, and additional cost to build TPM chips is a huge challenge. Another is a potential limit to the CAAB-based encryption is that it lacks maturity outside of a lab environment, being that it's this new novel thing. We don't know how well it's going to do in large scale networks. There's limited research to investigate firmware modification attacks, at least recorded. Utilizing AI, ML, deep learning, and quantum dot also add additional costs to lightweight IoT devices. And then lastly, proprietary architecture solutions or using too many different programming languages for these IoT nodes and various vendors working together at the edge really raises a concern for secured unified solution.
So this section will explain our conclusion. We shared multiple approaches with you on edge security. However, they lacked a unified framework with a layered security model. And that's what we're showing here. We're showing a strong security mindset that has developed a unified framework with layered security based on the research that we did. This will be a key enabler of edge computing. The start of the framework provides the trust model we discussed, along with 5-layer security using RF hopping. A layer for private blockchain is recommended, and that's going to increase security on the public key infrastructure. It's recommended to leverage quantum computing in future models to aid in private blockchain and machine learning. There's a machine learning layer, a subset of AI, which will allow our model to provide predictive analysis for proactive security with AI. Machine learning will process the vast amounts of data required that is beyond today's functionality. Reducing channel and adding CAAB in edge devices will reduce the actions of malicious users. Finally, SDN, NFV, this layer is coming to all networks that aligns well with cloud edge computing as discussed. And this is our SDN NFV right here. That's one of the most important layers that we feel. The network will become virtualized, and that's going to offer the agility, automation, and rapid response our security proposal warrants. The layered approach will provide better defense against vulnerability attacks, malware, SQL injection, denial of service, eavesdropping, phishing, weak passwords, zero-day, botnet, scripting, weakening public key infrastructure, unauthorized privilege abuse attacks. So quite a list of things that it will combat. And while the layered model offers the most secure environment, it does come at a cost. Since all IoT devices are lightweight, standardization will be important to drive vendor acceptance here. And that's where that acceptance will drive functionality for TPM, the blockchain, and the additional storage requirements that we shared with you. While blockchain and CAAB may be challenging today, it is our recommendation to implement these methods as future technologies become more mature. And then finally, the SDN NFV with cloud integration may add complexity to the network, but is the best way to achieve the agility and scale in the secure edge computing network. And I'll send it back over to Keith to close us out.
All right, so we're just gonna leave a reference slide here for you guys. If you wanna go back, feel free, we can send you the slides after. And then moving on. We wanna say thank you to Dr. Kaboush for putting on this class for us. It was a great learning experience for Steve and myself, and just an opportunity to partner with different people in different industries and learn a lot about something new. So thank you, Dr. Kaboush. And thank you, class. If we go to the last, yep. Thank you, class, for sticking with us for this presentation. Again, if you have any questions, concerns, feel free to contact myself or Steve on the topic, and we'd be more than happy to share our knowledge.
Yeah, absolutely. Share your feedback and your questions. We're excited to hear what you have to say about our presentation. And so this concludes our presentation. Thank you.
Thank you.